In the vast majority of automotive manufacturing, paint serves a dual purpose: aesthetic brilliance and structural concealment. It hides the microscopic inconsistencies of the substrate below, masking the inevitable variations of mass production. But when a client orders a Bugatti Chiron in naked carbon, that safety net vanishes. The clear coat offers no refuge for error. Instead, it acts as a magnifying glass for the slightest deviation in the material itself. Now let's open the factory blueprints and deconstruct the story of the Supercar engineering apex. The engineering problem here is not merely about surface finish, it is about the fundamental geometry of the weave. Standard carbon fiber production focuses primarily on strength-to-weight ratios, where the orientation of the fibers determines structural rigidity. However, Bugatti demands that this structural orientation also serve as an unbroken optical line. When we analyze the sheer scale of the Chiron's rear fender, a massive single-piece component, we realize the immense difficulty in maintaining a perfect 45-degree weave angle across complex compound curvatures. The challenge is unforgiving. A misalignment of the fiber weave by even a single millimeter disrupts the light reflection, destroying the visual continuity of the car. Unlike steel or aluminum, which can be filled or reworked, a cured carbon panel with a distorted weave is terminal. It cannot be fixed. It must be destroyed. This dictates a layup process of agonizing precision, where the craftsman is fighting the natural tendency of the fabric to distort under its own tension. We are looking at a manufacturing zero-tolerance policy where the aesthetic standard is as rigid as the chassis itself. The transition from the structural layup room to the paint shop typically implies a reduction in engineering risk. But inside the Molsheim facility, the danger curve remains critically high. The environment shifts from a fabrication floor to something resembling a semiconductor clean room. Here, the panels undergo a transformation that is less about addition and more about precise, calculated subtraction. The manufacturing hunt in this context is the pursuit of optical flatness, a state where the surface topography is so uniform that it ceases to interfere with light. The process begins with the application of the clear coat. This is not a standard automotive lacquer. It is a high solids resin system designed to bond chemically with the epoxy matrix of the carbon fiber. The technicians apply multiple layers, building up a thickness that far exceeds standard mass production specifications. However, this application is merely the raw material. For the true labor, once cured, the surface presents what is known in the industry as orange peel, microscopic undulations caused by fluid dynamics and surface tension during the drying phase. In a standard luxury car, this is accepted or minimally corrected. For the Chiron, it is an unacceptable defect. This is where the clock starts on the famed 300-hour finishing cycle. We might ask, in an era of 5-axis CNC machining and robotic polishing arms, why rely on the inconsistency of the human hand? When we analyze the thermal dynamics of polishing, the answer becomes clear. Robotic buffers generate consistent, localized heat. On a metal panel, the substrate dissipates this heat effectively. Carbon fiber, however, is an insulator. Excessive heat buildup from a robotic arm could soften the resin matrix, causing the weave to shift or the clear coat to delaminate. The human hand provides the necessary tactile feedback loop, sensing drag and heat in real time. The technicians engage in a grueling regimen of wet, sanding, utilizing progressively finer grits of abrasive paper. This is a reductive process. They are physically removing the clear coat they just applied, shaving it down by microns to achieve a perfectly level plateau. The tension in the room is palpable because the margin for error is razor thin. If a technician sands too aggressively and burns through the clear coat to touch the actual carbon fiber weave, the refractive index is shattered. The fibers become abraded, turning a milky white. At that point, the optical integrity is lost, and the entire panel, worth tens of thousands of dollars, must be scrapped. As the sanding gives way to polishing, we witness the emergence of the depth effect. This is not magic, it is physics. By creating a perfectly flat entry surface, the clear coat acts as a flawless lens. Light enters the resin, travels down to the carbon weave, and reflects back without scattering. The viewer isn't just looking at the surface, they are looking through it. The 300 hours of friction serve to remove any obstacle between the eye and the raw engineering underneath. The isolated perfection of a single panel is meaningless if it fails the final. Integration, the ultimate validation, occurs during final assembly, where the optical continuity must withstand the reality of complex panel gaps. When we examine the chassis centerline, we find the distinct herringbone interface where the weaves from the left and right hemispheres meet. This is not a chaotic intersection. It is a calculated convergence. The weave must flow seamlessly from the bonnet across the A-pillar and into the iconic C-bar, despite these being separate structural components manufactured weeks apart. We are looking at 8 distinct layers of carbon fiber that must visually behave as a singular organism. Achieving this requires an assembly tolerance usually reserved for internal engine components, not exterior bodywork. The technicians are not merely bolting on fenders. They are aligning a geometric grid across a 3-dimensional void. This alignment transforms the vehicle from a collection of composite parts into a cohesive demonstration of material mastery. The legacy here is one of absolute transparency. By refusing to use pigment, Bugatti removes the ability to hide every intersection, every overlap, and every fiber bundle is visible to the naked eye. It is a technical declaration that the chassis structure itself is flawless enough to serve as the aesthetic finish. We step back from the sterile lights of the inspection bay, realizing that true precision is measured in time and patience. The Chiron stands not merely as a feat of combustion, but as a victory of the human hand over stubborn, unforgiving materials. In a world of automated speed, there is something deeply profound about a surface that requires 300 hours of friction to finally reveal its true soul.